Okay, so hello everyone. Thank you for joining the Computer Science Department seminar. So today is my great pleasure to introduce Dr. Tuo Zhao from Georgia Tech to visit us virtually and give this seminar talk. So Professor Zhao is an assistant professor in the School of Industrial and System Engineering at Georgia Tech. He received his PhD degree in computer science at Johns Hopkins University. His research mainly focuses on developing methodologies, algorithms, and theories for machine learning, especially deep learning. He is also actively working on neural language models and open source machine learning software for scientific data analysis. He has received numerous awards, including the winner of the INDI ADHD 20 Global Competition. I think this is a competition for neural image. ASA Best Paper Best Student Paper Award on Statistical Computing, Informs Best Paper Award on Data Mining, and the Google Faculty Research Award. Okay, so please join me in welcoming Professor Zhao to give this talk.
Okay, thank you for the introduction. So it's really my pleasure to give this talk at UCLA. So today my talk is about the fine-tuning of pre-trained language model under limited or weak supervision. Okay, so the talk is based on my joint work with my student at Georgia Tech and Hao Mingjiang, Chen Liang, and Xiaoping E, and also my colleague Tuo Zhao at Georgia Tech and his student Yueyu Ruijia Wang, and also researchers from Microsoft, Peng Zhenghe, Xiaodong Liu, Jianfeng Gao, and Weizhu Chen. Okay, so let me start with the background. Okay, so we all know like deep learning has been super successful in the past few years. It's dominating applications in various fields, like including computer vision, speech recognition, natural language processing, etc. But we also notice that training deep neural network models, deep learning models, usually require a large amount of label data for training. So for example, for machine translation, so we have this WMT dataset. So considering this English to French translation, so the training data has 35 million sentence pairs. And for image classification, let's consider ImageNet. So the latest ImageNet contains 14 million labeled images. And for speech recognition, this library speech dataset contains 960 hours training data. So all of these just require a lot of human labor to annotate the data. So we say like deep learning models are label hungry. But the label data actually, unfortunately, they are expensive to obtain. For example, let's consider this this face recognition or face detection tasks, and then this is so-called AI annotation factory in China. So there are about like 10,000 plus workers in the factory, and they are labeling the face with 29 key points, or I think also called landmarks on the facial images, and each of them receive like $700 pay per month. You see, even like labor in China is already relatively not that expensive, but it still costs a lot to get this labeled data. And for natural language processing, actually getting labeled data is even more difficult, because when you get label data for natural language processing, actually the human labor, the human worker needs to know, needs to have some linguistic background, because the annotation actually requires linguistic knowledge. And also, I mean, when people do annotation, they need to use some expensive software. Like this one is called Prodigy. So it's a $409 per license. I think this is per year price. So overall speaking, just the NLP data, labeled NLP data is even more difficult to get and even more expensive. Okay, So some existing work suggests that for natural language processing, we can use some domain knowledge or some linguistic knowledge to generate so-called weak labels. So for example, let's consider this example. We can use the keywords in a sentence to label that whether this sentence is representing positive feeling or negative feeling. For example, the first one, my experience so far has been fantastic. So this fantastic is a positive word. So we can say, then we can label this sentence as a positive feeling. And then the next one is my experience is awful. So awful is a negative word. And then we can label this sentence as negative feeling. But such a weak label generation might not always be correct. For example, this one, I have never been disappointed. But this is actually because of the keyword disappointed. So this tense will be labeled as negative feeling, but actually it's a positive feeling. And also like this one, I can get help from nowhere. So in this sentence, it does not contain like simple keywords to represent the feeling, whether it's positive or negative. So in this case, if we use weak label generation, just a simple linguistic rule just cannot annotate this sentence. So it will lead to missing annotation. So overall speaking, just a weak annotation or weak label generation will give you, in most cases, give you noisy and incomplete label. Okay, so another approach to reduce to make the natural language processing more label efficient is called transfer learning. So far, the most popular transfer learning in NLP is this so-called BERT. So it's a two-stage transfer learning framework for natural language understanding. So we have a source data, and these source data actually are large amount of unlabeled data. We can fetch them from like either the internet or some certain like books or books. So and then we train a super large language model in the unsupervised manner. And then just from this source data, we get a huge language model. And then in our target domain, just means in our target domain just means that we have downstream tasks. For example, we want to either do like a machine translation or we do natural language understanding. So we have some downstream tasks, but these downstream tasks may only have limited and noisy label data. So our goal is to adapt the source, the label trained in the source domain to the target domain. Okay, so this method has been very popular and dominating most of the leaderboards, well-known leaderboards in natural language processing, including Glue, Super Glue, and QA Squad, etc. So now let me explain a little bit in details. So in the first stage, usually we call it pre-training. So it's essentially unsupervised mask language modeling. Just we do this in the source domain, and the source domain contains cheap unlabeled data. Just we can, for example, the most popular ones so far include Wikipedia and also some books. And to train this language model over this cheap unlabeled data, we do so-called self-supervised learning. It's just essentially like we predict the mask token in the sequence. Just consider you have a sentence, you mask some token, and you just use the context to predict what has been masked. So this is called a mask language modeling task. And then the pre-training just train the language model using this self-supervised learning over this unlabeled data. Okay, so the language model include an encoder and also a mask language model modeling classification head. Okay, the second stage. Second stage is called fine-tuning, where we adapt the model we trained in the first stage, in the pre-training stage, to the downstream task. So what we do is we just do supervised learning with a warm start. Here, warm start, I mean, we initialize from the pre-trained encoder, and then replace the mask language modeling classification head with the classification head for our downstream tasks. And then we just use this new model as the initialization. And then, for example, we can do just SGD to adapt this model to the downstream data. And the training only involves the data in the downstream tasks. Okay, so today my talk is mainly about like how to make the fine-tuning stage more effective and more efficient, and in a principled manner. So I will cover two cases. The first case is just when the targeted tasks only have limited supervision. What I mean here is actually we only have limited label data, just a small amount of label data. And another one is the targeted task with weak supervision. Weak supervision means that we are using some linguistic rule to generate the weak labels. And with those noisy and incomplete weak labels, and we do fine-tuning. Okay, so now let's first start with the limited supervision. So let's still go back to the pre-training. So pre-training, as I mentioned earlier, uses extremely large language models, and also using extremely large data. So here are a few examples. Now let's take a look at this example, BERT large. So this BERT large model contains 335 million parameters. So this is a huge model, much larger than the model we use in computer vision. So in NLP we use much larger model. Okay, and then this model actually is trained using some books and Wikipedia data, and the data size is about like 20 gigabytes. So this is
we got a question from the audience. You can see it Q&A. So the question is, what is a head in your previous slide?
Head is actually just a layer. You consider have an encoder converts the sentence into embedding, and then we feed the embedding into like just one layer of neural network with a softmax layer. Then we can do classification.
Okay, thank you.
Okay, so this is a BERT large, and you can see this Robert large is just improved BERT by slightly changing the model, but meanwhile they also significantly improve the training data size. So this one is 160 gigabytes, and for this T5, it contains 11 billion parameters and trained over 745 gigabytes data. And this GPT-3 contains 175 billion parameters and trained over 45 terabyte data. So basically we have enormous data and extremely large model. Now let's take a look at the fine-tuning stage. So fine-tuning stage essentially adapts the extremely large model we get from the pre-trained stage to a much smaller data set. Just consider here, I'm considering like 5 tasks from the GLUE data. So these five tasks, you can compare the data size. The largest one is this MNLI. It's only like 390 megabytes. And for the smallest one, like this one, WNLI, it contains only 98 kilobytes. So you can see, compared with the data we use for pre-training, the data here is much smaller. So what would happen in this case? Just as what we learned in the machine learning textbook. So we are using an extremely large model to fit extremely small data. Just if we are not train the model, if we cannot train model well, it will lead to overfitting. Actually, that's exactly what happened here. Just if you use that large model to adapt to these tasks, and you use aggressive update, you will quickly overfit the training data. and then forget the knowledge from the pre-trained model. Because our goal is actually just the transfer learning is essentially transferring the knowledge in the pre-training to the downstream tasks. But by doing aggressive updating, we will quickly overfit the data and forget the language, forget the knowledge. Okay, so to prevent overfitting, so existing methods usually use the following heuristics, like they use small step sizes, so extremely small step sizes, and also they can do layer freezing. For example, they just freeze several layers in the encoder, and only allow the algorithm to change the other layers. Or you can do multitask learning, just which means that you just tune the data, you tune the model just over multiple tasks simultaneously. So this is also kind of essentially kind of increase the sample size. But all of these, I would say, like they are tuning inefficient and lack of principles. And sometimes they work and sometimes they don't. Okay, so basically just these are the drawbacks. So our goal is to like overcome these drawbacks and then improve the fine-tuning stage. So someone may ask the question that why not improve the pre-training stage? Here, just I would say like the fine-tuning stage actually require much less computational resource than the pre-trained stage, which is more friendly to academia, where we don't have just expensive GPU server. Okay. Okay, so the method here I'm going to introduce is called SMART. So this is to improve the fine-tuning with limited supervision. So it contains two ingredients. The first one is called smoothness inducing adversarial regulation. And this regulation can help control the model complexity. And later in experiment, we will also show that this regularizer actually can also help capture the ambiguity and improve the robustness. And the second ingredient is Bregman proximal point optimization. It's an optimization algorithm. So this algorithm will prevent aggressive update. And also it can adapt to the underlying just information geometry of the problem. Later we will discuss this. Okay, now let's first take a look at this adversarial regularization. So this adversarial regularization, we define it in this way. So here F is a model with the input xi and the parameter theta. And this x tilde I is a perturbed input. So here we define x tilde I is just stay in a ball centered at xi with a radius epsilon. So here I'm in L infinity ball. And then we do this maximization over this LS. This LS is symmetric, measuring the discrepancy between fxi theta and fxi tilde theta. And then eventually and then eventually take summation over all the data points. So this is our smoothness inducing adversarial regularizer. So it's actually involved a maximization problem. Okay, so the training objective is just we minimize the loss function over the training data plus this regularizer, and this lambda s is a tuning parameter. Okay, so what does this smooth inducing adversarial regularizer do? So it's actually encourage we call smooth model output. So by smooth model output, we mean if you slightly perturb the input, then we want the output of the F remain similar. So for example, this is the input and this is the output. So if we perturb the data and the output leads to this Y double prime, so Y double prime significant change from Y. So we say this model is not that smooth. Or Y only changes to Y tilde, Y prime. So the change is relatively small, we say this is a smooth model. So this is called a smoothness. So this
can I have a question about this? Yeah. So I wonder this perturbed embedding metric. Is that something similar to the, for example, the Kell divergence between this F on the original data and F on the perturbed data, similar in the, for example, traits, which is an adversarial training algorithm, or do you use something else for this LS magic?
Yeah, actually here we use Kell divergence or symmetric Kell divergence. Just the form is the same as a trace, and later I will explain like the difference with the trait.
Okay, thank you. And another related question is, if you recall the example you showed to us at the beginning of your talk, so there are many like a sentiment or review sentences written by different users. So if those, for example, labeling process highly depends on some keyword. For example, if it is a positive word or if it's a negative word. So if we do this kind of a perturbation in terms of L infinity distance, would it, for example, happen to just perturb the, for example, the good word to be a bad word? And in this case, the Kell divergence, in this case, the L infinity distance is still small, but the label is totally flipped. So, and if this happens, it seems that the illustration shown on this slide may not work. So do you have any comment or idea about this kind of situation?
So the first thing is that the adversarial. I didn't call it adversarial example because it does not actually, the perturbed xi tilde does not necessarily contain any semantic meaning.
Oh,
so you perturb the embedding, but the perturbed embedding, it might be difficult to find an actual token for this perturbed embedding.
I see. So that means that the perturbation on the embedding level does not perturb the original sentence. It may just like something not exactly corresponded to, for example, a change of word in the original sentence.
Exactly.
Okay. Thank you.
Also, the second thing is that later I will show that because we only do like one step gradient update, so this regularizer is relatively weak. So it's it's different from what we do for adversarial robust classifier. So it's a different story.
Okay, I see. Okay, thank you.
Okay. So here now let's go back to this this regularizer. So this regularizer essentially measures the local Lipschitz continuity under the metric LS. So you can see we just want to so this essentially just measures the output, the difference in the output, and subject to the input perturbation is within a small range. So this is exactly measuring the local Lipschitz continuity under the metric LS for the function f. And this concept actually, I did a little bit of research, literature survey, and I found that this concept actually dates back to the local shift sensitivity in robust statistical literature. So the earliest one is in 1974, and the definition is just almost the same. Okay, and then here we just use it to so this regularizer just in this paper they use it to promote the robustness, but here we mainly use it to control the model smooth complexity. So we want to generate some smooth model.
Oh, sorry. Question here. Sorry, can you go back to the previous slides?
Okay.
So I'm wondering, because I know that this adversarial regularizer is motivated from adversarial training, and I think my question is that why do you need to use the infinity norm? To my understanding, in computer vision research, people usually use the L infinity norm because they just want to perturb the pixels. But this is different for NLP because currently you just consider like the embedding of the the sentence or the graph or the paragraph. So I'm thinking, why do you need to use L infinitive perturbation rather than L2 perturbation?
Oh, here I only use the infinitive as an example. Just actually, you can replace this any other node. And what we show actually something very. So for machine translation, actually, I think 2-norm actually works better.
Okay.
But for the natural language understanding task, this is only my own experience. Infinity norm works better.
Okay.
Yeah. So in general, we don't have.
So the choice of norms will be different for different tasks.
Exactly.
Okay. Thank you.
Okay. So with this regularizer, actually we can generate. So here is one example. This is just a simple classification problem. And then if without using the regularizer, we will see it generate like some not very smooth decision boundary. So you can see there is a sharp transition here. And if with this regularizer, it will generalize a smoother decision boundary. Okay, so here just I want to mention again that the adversarial example in this case actually do not necessarily have semantic meaning, and also we are not using it to train the adversarial robust classifier. We don't want the classifier to be robust to some kind of adversarial example. We just want to improve the generalization over the clean data. So that's the different that's the major difference from trace, because trace, if you are familiar with trace for training a adversarially robust classifier in image classification, that one aims to improve the generalization over the adversarial examples. So here is the key difference. Okay, so now I want to also want to mention a few related works. So this adversarial regularizer actually, the earliest one, I mean, literally, the earliest paper about this adversarial regularizer actually is this Miyato 2016. They use this adversarial regularizer for semi-supervised learning. And later, this Zhang 2019, and they use the same regularizer but for training adversarially robust classifier. And then this Xie, they use this regularizer for some unsupervised domain adaptation. And more recently, this is my SML paper. So we are using this regularizer to control the smoothness of the policy in deep reinforcement learning. Okay, so these are just the related papers, but used for different purposes. Okay, so that's about adversarial regularizer. And the second ingredient of SMART is called Bregman proximal point optimization. So here, Bregman proximal point optimization, just in short, BPP. BPP try to prevent aggressive update by iteratively inducing trust regions. Here, trust region means that at each iteration, we only search within a small neighborhood of the previous iterate. So think about this, just at tth iteration, we take theta t plus 1 equal to argmin theta f theta. But this theta and theta t, the Bregman divergence between these two needs to be smaller than beta. So here is the definition of Bregman divergence. So we just use some metric LS to measure the fxi theta and fi theta t. So this Bregman divergence in this constraint essentially just introduce a small neighborhood around theta t, and we only allow the algorithm to search within this small neighborhood, so aggressive update won't happen. But this constraint form is actually not that computationally friendly. So we adopt this more convenient just regulation form. So instead of using constraint, we just change it to a regularizer. So this will serve the same purpose. Okay, So
sorry to another question related to this Bregman proximal point optimization. So why do you use proximal point algorithm rather than proximal gradient algorithm? So in other words, why don't you linearize the, for example, the object function f of theta, just like what people are doing more frequently in practice? So is there any specific reason that proximal point algorithm is more favored in this situation than proximal gradient helps?
So I would say like so if we so the first thing is that if we only do like one step gradient update, this will reduce to the mirror descent, something like mirror descent, right? Here we do multiple step. So I would say like more like a practical reason. So we find that in practice you use proximal point, just you have you can achieve a little bit better performance.
Okay, so you are saying that the implicit update is better than the explicit update. Can I understand it in that way?
I think so. Yeah, and so far just because this objective is very complicated, so I cannot say like for sure what's happening. But but my experience that this proximal point method is usually more effective for yield condition problem.
Okay, thank you.
Yeah. Okay, and another advantage of this Bregman proximal point optimization is actually because of this Bregman divergence as a regularization, actually it can adapt to some underlying just the information geometry of the problem. For example, here consider classification problem. So the classifier always output a simplex. So this simplex can be considered as some kind of just manifold. We are doing optimization over some manifold. So this KR divergence will this Bregman divergence will help the algorithm adapt to the underlying information geometry. So it will give us like a better computational performance and also even also a better prediction performance. Okay, and here I'm providing an alternative perspective of Bregman proximal point. So if you are not familiar with optimization literature, you can view this one as a so-called student-teacher framework. So here we can consider like the student model as this t+1, so the iterate we get from by minimizing this problem. And this theta t, just the parameter from the previous iteration, can be viewed as a teacher. So in every iteration, we would like the student should not deviate too much from the teacher. Okay, so this is the student-teacher explanation. Just if you are familiar with semi-supervised learning, and this is just one framework people usually adopt. So and also just besides just choosing theta t as a teacher for the t+1 iteration, we can actually do the exponential averaging. So the exponential averaging just actually yield something called a mean teacher, and this is equivalent to the momentum update in optimization literature. So this we will use this mean teacher just in this Bregman divergence, and then minimize this objective. Okay, so now let's take a look at some experimental results. Okay, so we tried our we tried our excuse me. Okay, so we try our smart method on glue data, and here are some results. Just among all single models, we can see smart actually this is a glue average score on the test data on the test set. So smart attained 88.4, and compared with other single model, we can see BERT is 80.5, and multitask pre-training give us 82.7. And this T5 is a huge language model. contain actually 11 billion parameters, and it achieved the score, average score 89.7. Okay, so this is a single model. And on GLUE leaderboard, people also compare like an ensemble model. And here you can see this one is Robata, and the score is 88.5. Free, this is free LB 88.8, Alice 88.89, Albert 89.4, and here Smart achieved better performance than these guys. So we have 89.9. So for those of you who are not familiar with GLUE leaderboard, so GLUE is actually GLUE contains a collection of natural language understanding tasks, including I think the sentiment analysis, what's that called, language inference, and also question answering, just a bunch of tasks. And here the average means that this is the average score of 9 tasks, I think. Okay, so so our Smart actually was on the first place, like from December 5th, 2019 to January 16th, 2020. And also here are just more details. We compare the performance of Smart with others on these just on these tasks. So here is the performance on the development set. So basically, just Smart actually use a smaller model and achieve just better performance. And also, we also do some ablation study. So here is the result. Here is the result of using both adversarial regularization and the proximal point optimization. And we can see actually both Bregman proximal point optimization and adversarial regularization actually improve the performance. And they are both effective and they are complementary. And we also find that Smart actually achieve like more significant improvement on the tasks with small data. For example, this RTE and this MRPC. So their data sets, their data are even smaller than the others. And okay, so here is an additional benefit. Just in this MNLI data, so we find that the Smart also help capture the ambiguity. So here is one example. So this MNLI data set is actually it contains 3 classes, but for each sentence, there are 5 annotations. So annotated by 5 different persons, and because there's some ambiguity in the data point, so these 5 persons may not give you exactly the same annotations. So you can see here there can be some disagreement. So this one is 500. So here the number just means this there are 5 persons all agree that this belongs to the first class, and this one 410 means that 4 agree it belongs to the first one, and 1 agree it belongs to the second. So there's some ambiguity in the data. Now let's take a look at this one, 320. And you can see in terms of the classification accuracy, actually the Robata without our Smart method actually achieve better classification accuracy. But if we compare the KL divergence between the output of our model, actually we can see in terms of KL divergence, actually ours achieve better results. So this is why we argue that it's actually better capture the ambiguity.
Hi, Professor. Can I ask a question here?
Okay.
So back to your previous comparison with other baselines. I know that FreeLB is kind of similar to adversarial training, and you mentioned that Smart is also more similar to trace, right? So my question is that in image classification, like traces generally achieve slightly lower natural accuracy, but achieves better robust accuracy here. But for this language modeling task, since we are only carrying the natural generalization, I wonder if there any other trade-off exist, or it is just always better here for using this smoothing induced regularization here.
So there's one thing I want to mention, that trees actually does not necessarily achieve worse performance on the clean data. It only happens that when you do not tune the regularization parameter, because trees contain two parts, the loss and the regularizer, right? And there's one additional regularization parameter. And by changing this regularization parameter, you can either make the trace favor adversarial robustness or the accuracy on the clean data. So
I see.
Yeah. So here, just I think the similar things happen here. Just you need to tune the regularization. And here I want to mention a little bit. Yeah, just we can discuss offline. Just in general, my experience is that this adversarial regularizer in this case, it's called virtual adversarial training. This virtual adversarial regularizer actually outperform standard adversarial training. Actually, in most of the cases, we have done some experiments, and we eventually find that this virtual adversarial regularizer is better in many cases. So we can discuss this later after the talk. Okay, so so this one is about the robustness. So here, just I'll skip the details because here it involves another paper. This paper used some iterative method to generate some hard example for natural language inference. So, but overall, the message here is just that we find that the smart actually can improve the robustness of the model, and also it can improve it can help domain adaptation also. Just if you are interested in these results, you can refer to more details in the paper. Okay, and then I'll talk about the second part. So the weak supervision. So here in weak supervision, I'll consider the task called named entity recognition. So this named entity recognition is just trying to find the named entity in the sentence. For example, this one, Thomas joined Georgia Tech in 2018, and here the named entity includes the entities include the Thomas as person, Georgia Tech as organization, and 2018 as time. And here we will use the weak supervision, and a natural, natural weak supervisor, weak supervision source we have is the Wikipedia. And when we use Wikipedia, you will find the Wikipedia has annotations for different entities. So here is one example. So let's say this sentence: Liverpool is a famous football club in Liverpool. And there are two Liverpools, and both of them actually can be found in Wikipedia. So one is the places. So it's a city in England, Canada, US, and also actually in multiple states of US. And it can also be a football club. So soccer football teams in UK. And actually, you can also find that I think there are some album or some movie called Liverpool. Just basically, you can find a lot of annotation in Wikipedia for this Liverpool. And but for this introduce like a ambiguity to the named entity recognition, to the NER. And also there are also many other entities which are not covered in Wikipedia. So basically, what I'm saying here is the Wikipedia is exactly as what we have described. It generates weak labels, but noisy and incomplete. Okay, so there have been some existing methods for doing NER, just using weak labels. And one is this auto NER, and the other is LRCRF. And but all these existing methods, they require accurate knowledge base of specific domain. For example, both of them, in both papers, they use their methods for in biomedical domain, because in biomedical domain, the knowledge base is usually there's usually less ambiguity and also just more complete than open domain tasks. So here I want several examples. So for biomedical domain, and these are two data sets. And if we use the knowledge base in these papers, you can see just by simply doing keywords matching, the F1 score is already around 72 and 70 for both data sets respectively. And the precision is even higher. Precision is 93. And this one is 90. But compared with open domain NER tasks, so F1 this one is around 60, and this one is around 35. And the precision is around 71, and this one is around 40. So basically, the open domain NER is a much more difficult task. And the weak supervision is actually just weak, really weak, not very reliable. Okay, so to handle the weak labels, the noisy, incomplete weak labels, we propose this method called BOUND, BERT-assisted open domain NER with distant label. So distant label is just one kind of weak label. Okay, so it contains two stages. The first stage is just a BERT-assisted weakly supervised learning. And we use the Wikipedia to generate the weak label, and then we transfer the knowledge from the pre-trained model to NER just by doing adaptation. And then we need this early stopping. I will explain later just why we need this early stopping. Okay, the second stage is self-training. And in this self-training, we actually drop the weak labels we obtained in the first stage. And we do some kind of pseudo label reweighting to generate the pseudo label, and use these pseudo labels to train the model. So it's essentially like generating some labels to train the model itself. So that's why it's called self-training. And also we use this high confidence screening, which I will elaborate later. Okay, so this is the two-stage paradigm. Stage 1 and stage 2. Okay, so now let's first take a look at this first stage. So first stage is just a standard fine-tuning. We start with we have this loss function, and here DM denotes the distance label, the weak label, and this XM denotes the input sentence, and F is the NER model with parameter theta. And we initialize the F with the BERT encoder, and then replace the mask language modeling classification head with the NER classification head. So here, one important thing is the early stopping, because we know that the weak labels actually are noisy. So if we allow the fine-tuning stage if we allow the fine-tuning, if we do not do early stopping, this fine-tuning will just start to overfit the weak labels. So let's see, this is the initial. So this one is the initial. So the initial encoder and the classification head might not give you a good performance, but with the adaptation, and we can see it start to perform better. But if we do not stop here and continue the fine-tuning, we will see this eventually this model will just overfit to the weak labels. Okay, so to prevent weak overfitting, we just do early stopping. The second stage is self-training. Here, I'm also using the student-teacher framework to explain self-training. So you can consider it's still iterative. So at every iteration, we first use a teacher model to generate some pseudo labels. So this denoted by ym tilde. And this ym tilde is actually just the output. It's based on the output of the teacher model. So if we use argmax rule, we will get a hard label. If we use just the identity, and we will get a soft label. So the probability simplex. Or later, I will show that we can use other rule to generate the pseudo label. Okay, and then the next step is to train student model based on the pseudo labels generated in step 1. And then we update the model and then get a student model. And then we just replace the teacher model by the student model we obtained in step 2, and then go back to step 1 and repeat this procedure again. So this is called self-training. So for pseudo label generation, just besides hard label and soft label, here we can also use this so-called reweighted soft pseudo label. So this soft pseudo label is generated in this way. So this FNC is actually means the it's for the sequence n, and the probability the sequence n at position m classified to class C. So this is the posterior probability based on the model output. And we take square and then renormalize it. So I know someone may think that this is a weird update. So usually, like many people would prefer, like for example, the exponential update. But here I want to mention that the reason we use this one because that we try many different updating rules, and this one gave the best performance. But in general, you can use like other rule, like exponential weighting. But the overall the high level idea is that we want this reweighting to gradually increase the confidence of the predict label. Consider a 2-class classification. So we may have an output like 0.7 and 0.3 for bi-class classification. 0.7 denotes the probability, posterior probability. The class label is equal to 1, and the other means the 0. And so by using this updating rule, and we can see after we take square, one will become 0.48 and 0.59, and the other becomes 0.09. And after normalization, the probability the probability that the label belongs to the class 1 will actually be increased actually above 0.7. So this reweighting procedure is essentially just gradually increase the confidence. But we also don't want this the increase in the confidence to be too aggressive. Sometimes sometimes the exponential reweighting just give a too aggressive increase. So to avoid this to happen, we use the square update. Okay, and then the other trick we used in this self-training is called high confidence screening. So basically, just we want to keep those tokens with high confidence, which means that if the model is not sure about the one token, then we just ignore it. So this is based on a common belief that unconfident tokens are just hard examples which are difficult to predict. So by introducing them in the training, we will only increase the variance. It will not help prediction. So that's why we drop them. So this is called high confidence screening. Okay, and now let's take a look at the experiment. So we can see this is the Kono 03 dataset and Wikigold. And by knowledge base, just keywords matching, the F1 score is 71 and it's 47. And if we just use standard, if we use existing method, for example, this auto NER or this LRCRF, you can see actually the NER performance actually drops after training. So which means that when your labels are very weak, just contains a lot of noisy labels, and the training does not necessarily help. Excuse me. Okay. Okay. So stage 1 we have 75. Just after stage 1, just the performance is improved to 75, and this one on Wikigo improved from 47 to 51. And if without the pre-training, model, just we randomly initialize the encoder, you can see the performance is very bad. So this method will not work without the pre-training, given if the language model is large. Okay, and then if without early stopping, and you can see the performance is also worse than the performance with early stopping. Okay, then stage 2, and we can see after stage 1, the performance is around 75, and the stage 2 further improve to 77. And if we further use the soft label reweighting and also the high confidence screening, and we can further improve it to 81. And on Wikigo, we can improve it to 60. And here is a more comparison over over 5 data sets. And we can see our method actually achieved the best performance uniformly over 5 data sets. Okay, and then at last, I'll just quickly mention more recent related results. The first one is that we further extend this adversarial regularizer technique, and we use another form of just adversarial regulation, and we show that the new regularizer can help improve the out-of-domain detection, which means that if you do classification, for example, binary classification, and here what I mean improve out-of-domain detection means that if you are using an out-of-domain sample, and the classifier tends to give you the output 0.5, which means that the model is highly uncertain about this sample. It could be out-of-domain data. So then you can reject this sample without doing classification. So this is what I mean by improving out-of-domain detection. And it also improves the in-domain model calibration, which means that in this paper, we found that BERT often suffer from so-called overconfidence, which means that the prediction could be wrong, but the model still gives high confidence. So in this case, we want to calibrate the model output. So if the model is uncertain about the data, then the classification is likely to be wrong. So this is called the probability calibration. Okay, we find that adversarial regulation can also help this case. And in another paper, we improve the self-training and propose the so-called contrastive regularized self-training. Just we find that the contrastive regulation actually can also help improve the self-training. So this paper is now on arXiv, and this one is on it's in EMLP. Okay, so here let's summarize. So I have a few take-home messages. The first one is the adversarial regularization actually can effectively control the intrinsic model complexity. And the second one is the Bregman proximal point optimization can prevent from aggressive update. And then the self-training can reduce the error propagation of the weak labels. And our method can be naturally extended to semi-supervised learning and supervised learning with noisy labels. Just we have some experiment in this paper. And also just we can actually extend our method to applications beyond the natural language processing. So including computer vision. So this paper is a concurrent work to our SMART paper. They show that adversarial training can improve the generalization over the clean data in image classification tasks. And here is another paper, just our paper in SML 2020. So it shows that the adversarial regularization can also improve the deep reinforcement learning. And here are the references. Okay, so question?
Yeah, thank you. Thank you for the great talk. Now let's take some questions. So maybe first of all, let me read several questions raised in the Q&A. So I can read the question for you. The first question is from Katie. How does smoothing the model output help with fine tuning?
Let's see. So this I assume they're talking about the smooth the model, right? Just the smooth the output.
Yes.
So here, smooth the output is essentially control the flexibility of the. You can think about this way: it's controlling the flexibility of the model. So the model cannot be too flexible, right? Just basically the slight change in the input only leads to just a moderate change in the output. This itself is just a control the complexity model just by its nature. Just
right.
So I hope this answers the question.
Yeah, but how does it help the fine tuning process?
Because fine tuning actually we start with so here let me say a little bit more. So when you have so consider the pre-training stage. We have large data and a large model. So because the data actually, I would say, comparable to the model size. So in this case, we train the model, we will end up with a smooth model.
Right. Oh, okay, I see. So it's like a fine-tune the model to make it more smooth.
So what I'm saying that the pre-trained model is smooth at the beginning, but when you do fine-tuning, it starts to become less smooth because it overfits to the data of the downstreaming task.
Okay, I see.
So we want to preserve its smoothness. So that's why we use this regularizer.
Okay, so you want to start with a smooth model when you do fine tuning.
Yeah.
Okay, thank you. The second question is from Lu He. So the question is, when you show the advantages of your method in GRU score, you only use your method in fine tuning process, right? So so basically, the student asks you whether you only use your method in fine tuning process for the GRU leaderboard. And the follow-up question is the pre-trained model are the same across different competitors. So in other words, for all these different baseline methods, do they use the same pre-trained models to start with, or they are start with different pre-trained models? So here are two questions.
So this Robota actually, so here our SMART use Robota large as the pre-trained model. And here also the same to this Robota large, and free LB. And also Alice. And this Albert use a different architecture. But this architecture here, although it shows that the size is only like 235 million parameters, but actually it's equivalent to 3 billion parameters because it's do some parameter sharing. So you can consider this Albert is actually a much larger model.
I see.
And these are about the same. But but here, pre-trained model does not necessarily mean that. So they start with the same pre-trained model, but this Alice, I believe they also use additional data. So they do something called a continual pre-training, which means that they are not only pre-trained over the over the original data set. They also pre-train, continue to pre-train it over another data set. So I think in Alice, they use some additional data.
I see. Yeah, that's
yeah. And there's also one thing I want to mention that for the ensemble model, actually we only do just a very little ensemble. I think it's just here among 9 glue tasks, we only do ensemble for 2 tasks. And for the others, I believe they are doing ensemble for just more tasks, more than ours. Okay.
Okay, thank you. And the last question in the Q&A is from Haiying Huang. So the question is adversarial regularizer and the proximal updates applied here? I think the question is maybe in the last part of your talk. Have you applied adversarial regularizer and the proximal update for this?
Here, I want to show you that. Oh, it's not here. Okay, actually, what we find is that adversarial regularizer and the Bregman proximal point optimization is not that helpful when you have weak labels. Which means that when your labels are noisy and virtual just adversarial regulator and Bregman proximal point actually they cannot give you. We believe it cannot give you the desired promise because the main bottleneck come from the noise in the label. So self-training is a more effective way to reduce the noise in the noise label.
I see. Thank you. Okay. Now let's take more questions from the audience. Yeah, so please raise your hand if you have any questions. And I will unmute you to ask you to speak.
Oh, hi, Tuo. So I have a question about the early stopping. So I'm wondering what kind of stopping criteria do you use to perform the early stopping?
So this one is a bit, I would say, like so we just do some tuning to check. Just there's really no way to precisely tell you that one is early, one is late.
I see. So is this something like using some validation data or just?
What I can tell you is so I remember like usually just when people do fine tuning. That's the I would say that's our experience. Usually we do not do over 5 epoch. So I believe we only do like within like 5 epochs. Usually not very large. But we find that for this NER task, even 5 epochs are just simply too large. So I think we only do like 2 epochs and then we stop. So that's why we call it early stopping.
I see, thank you. So actually, I have another question related to the previous question. So about the adversarial regularization, I'm wondering whether it can be kind of applied to more general setting, like just some general learning problem. Do you think it can kind of generally improve the generalization performance, or?
I would say it depends. So here I mentioned, we find that the adversarial training is extremely helpful, more helpful than the other cases that when you have small data. So for large data, especially we try, for example, neural machine translation. As I mentioned, like for some neural machine translation problem, we have a huge data, and we found that the adversarial training actually help very little in those tasks. So does that answer your question?
Yes. Okay. I see. Thank you.
Thank you. Yeah. So there's a more question. So let me okay. Now you can speak, Ru He.
Hi, Professor Zhao. Could you go back to that glue score results?
Yeah.
Yeah, so I have a follow-up question. So when you compare your method, SMART, with other methods, how do you get the glue score for other methods?
Oh, these are on the leaderboard.
Okay.
Actually, I would say like these are the results on December 5th. Actually, I don't know what happened, but if you check the recent latest result, I think free LB is only 88.4.
So then for your SMART method, how many epochs do you actually use in your fine-tuning process?
As I said, like in most cases, I think 5 is the maximum. Just we don't need to do more than 5.
Do you use DevSet to check whether you need to do the early stop?
Yeah, actually, yeah, we do use DevSet. Just actually the parameters is tuned over the DevSet. Also including the number of epochs, but we find that just 5 is enough, is sufficient. You don't need to tune more than 5 epochs.
Cool. Do you also use the grid search to actually search the hyperparameters, such as batch size, learning rate, something like that?
We didn't use very refined grid, but we did search the step size, and the details can be found in the paper.
Okay, cool.
Yeah.
Thank you.
Thank you. Is there any other questions from the audience? Okay, so if there's no questions, let's thank Professor Zhao again for this great talk. Thank you.
Thank you.